Thank you everyone for making it out today. I'll go ahead and go into the slide mode and let me know if everything is displaying properly.
Actually, it is other way around. Now it is great.
Now it's fine? Okay, very good.
Yeah,
So,
right.
Olga did a great job kind of giving a little bit of history of my beginnings into diamond surface chemistry, which was more bio-related. And so nanoscale diamond was needed to be able to sprinkle our NV diamond onto neurons. Right now, though, you'll notice that instead of it saying San Jose State, it says the City College of New York. And I'm here in Carlos's lab and learning an amazing amount about NV, photophysics, charge transport, and the like. But the title of the talk, Tuning a Quantum Nanoprobe, Advancements in Diamond Chemistry Using Halogens, Low-Z Precursors, and Metal Oxides. So I'll just get right into it, and we can begin the discussion. If there's any questions, just go ahead and let me know. Don't have to wait till the end to ask any questions, and I'll be more than happy to have that discussion. So let's go ahead and look at this unfinished yellow diamond right here. This is what we would see after you dig diamond out of the ground, and it's a rough stone, and eventually this rough stone will become beautiful, and we have that lovely yellow tone because of substitutional nitrogen inside of the diamond lattice. After we've cut it and polished it and done everything that we need, we could then be left with something gorgeous like the sun-drop diamond. The sun-drop diamond is the largest natural yellow diamond on the planet. It was only discovered in 2010, and for a measly 10 million, you can have the sun-drop diamond. Now, you don't get a feel for how large this rock really is. This is what the rock looks like on the human hand. This is a massive stone. But we're not here with Olga and team because we care about the big stone. We really care because of the nitrogen vacancy center and the ability to take that substitutional nitrogen and turn it into this quantum defect that is so essential for sensing, quantum communication, quantum cryptography, and the like. So I wanted to highlight when we go onto Wikipedia, and this is the Wikipedia website for the sun-drop diamond. Look what it says here, everyone. It says, the intense yellow color, or vivid fancy yellow as the experts called it, is given to the diamond by molecules of nitrogen that have been trapped in the molecules of carbon and hardened over thousands of years. Of course, I didn't know that carbon and nitrogen were molecules and that they are trapped in one another. So we need to change this Wikipedia page because this is not a rigorous interpretation of what's going on with substitutional nitrogen and diamond. But I think that's a nice aside. Don't believe everything you read on Wikipedia. And I digress. So as we get into the talk, I just want to have three broad ideas get across. One is that the surface chemistry with high pressure, high temperature nanodiamonds can be translated to bulk diamond. So what I'm talking about with nanoscale diamond should be applicable to our bulk diamond samples. We can also be more creative with our diamond chemistry. Instead of just using oxygen terminated diamond, let's take advantage of what we know from organic chemistry and other methods to really begin to tune our termination of the diamond. And so I asked this question in point number 3. Can we control diamond like a small molecule, similar to adamantane? Can we make it nucleophilic? Can we make it electrophilic? Can we clean the surface of electronic states which might be in the band gap? And so with that kind of preface, we'll get into the heart of the talk. Now, once we take that substitutional nitrogen, if it's adjacent to a vacancy and we add an extra electron, we've generated our nitrogen vacancy center, and Olga is an expert in creating these. But the NV center doesn't exist in just one charge state. It can be an NV0 with its own photoluminescence and NV minus. If we're in the NV minus charge state, of course, we've got this ground state triplet where we can initialize the spin and have a non-zero probability of going into a singlet dark state. And if a DC magnetic field in a microwave is on resonance with this transition between the 0 and +1 or -1 charge states, we can deterministically control that spin state. And therein lies the power of this whole entire system. At room temperature, we can have long spin coherence times and be able to extract important fundamental physics and use it for a number of applications, which I don't need to summarize here, but includes magnetometry, electric field sensing, thermometry, and many other things. So we need to irradiate the sample. So we need to generate these vacancies within the system. If the nitrogen is already there, we would irradiate with any number of different particles. If it was a super clean diamond, like a CVD diamond, then we implant with nitrogen 14 or nitrogen 15. We then have vacancies that are generated inside of the material. These vacancies will then percolate and move during our high temperature annealing steps, and we'll be able to have most of the vacancies actually get annealed out, but every once in a while the vacancy will land next to a nitrogen, and we'll have our NV centers now activated. And because they've got photoluminescence, we can go ahead and use our NV properties and confirm that everything has worked properly. The key, though, is what happens when the NV is close to the surface. Surface noise, magnetic spin noise, all of these things can then mess with that spin coherence time that many researchers are so interested in, especially if we want to do quantum sensing. So in lies the surface, where, of course, many negative things can happen. And of course, for quantum dots, which I spent many years researching, the surface was always important because we had a delocalized wave function which would interact with the surface. And so everybody knew that the photoluminescence properties and the charge transport properties, were tied to surface dangling bonds and defects. So in a nice summary slide of the great advancements that are happening in the Mariles lab, on the left-hand side, you can see work with electron and hole transport and capture. You could have arrays of NVs, which are then illuminated, and you can control the NV minus, NV zero charge state, and then be able to capture the mobile electrons and mobile holes through the diamond lattice. The work on the left-hand side was done by Arthur, and he's now down in Princeton working with Natalie De Leon, and they discovered this massive cross-section for the capture of the electrons in the holes. And then on the right-hand side, you've got recent work for the storage, the reversible storage of information within the electronic structure of the diamond done at cryogenic temperatures. So basically you would have hyperfine splitting of the states that I showed on the last slide, and you can be able to control the NV0 and NV minus charge state, and therefore the photoluminescence, and encode information within the same plane. And I think this is an important aspect. As you look from left to right, all of these images are encoded in the same XY plane, but the information is encoded at different frequencies. So you basically have the same plane with different pieces of information that are accessed through different frequencies of the shifting of your laser. So quite powerful information, and I highly recommend that everybody in the room check out these two papers that have recently come out. And I believe Richard is currently in the room, and of course he's an expert in the field. So when we think about diamond, not all diamonds are the same, and I think that's an important aspect. On the left-hand side, we have detonation diamond, which is a lower quality material. It doesn't host NVs as well. On the right-hand side, you have chemical vapor deposition diamond, which is of higher quality and it's more expensive. Now, for each one of these materials, of course, they have an all-carbon matrix. They should be non-cytotoxic and be chemically inert. And we know about their optical transparency, the high thermal conductivity, and high electrical breakdown. For today's talk, I'm discussing the high pressure, high temperature nanodiamonds, which Adamus provides, and that are more easily accessible if we have a bio-related application, using it in cells and tissues. But I want to make the point again that the information about HPHT should be translated to our more high purity, more expensive chemical vapor deposition diamond. So it's an exciting time for the field. Most routes use carboxylic acid chemistry for biolabeling and some of these quantum sensing applications. But I want to make the argument that HPHT, under specific conditions, mostly has alcohols. And these alcohols have a large bond dissociation energy, so they don't want to change very readily. And one of the grand goals of the lab is to tune these surface dipole moments, which then affect our NV photophysics. Can we control the charge density on the surface? Can we control the charge identity from positive to negative to neutral species? And more importantly, can we remove mid-gap states that cause decoherence of our NV centers? On the right-hand side, these are some images of silica-coated nanodiamonds that you might all be familiar with. So if we look at our HPHT nanodiamonds, we have some high-resolution TEM, and we can see that a vast majority of the facets are terminated with 111 crystallographic facets. We can do all of our characterization, looking at these edges and saying to ourselves, well, why are 111 crystallographic facets overexpressed within this material? And the answer has been known for hundreds of years by jewelers, but has recently been described by DFT. And so in this particular figure, we've got strain versus stress. And so we add strain to our diamond, and then eventually it fails due to the stress, and we have cleavage. First, it's the 111, then it's the 110, and then the 100. So during the ball milling process of macroscopic diamond, to make HPHT nanodiamonds, we're basically following the preferential cleavage of diamond in real time. But why do we care? Why are exposed crystallographic facets important? Answer, because the number of sp3 orbitals and their dangling bonds are available for surface moieties. The 111 crystallographic facet has a single dangling bond, while the 100 has two dangling bonds, and therefore should control the number of carbon-oxygen bonds that are formed. The difference between an alcohol, an ether, an aldehyde, a ketone, a carboxylic acid, so on and so forth. So this material looks like this as we get it from the manufacturer. This is the bulk version. This is after ball milling. And then we can go ahead and remove the amorphous carbon and purify the material using Raman spectroscopy, X-ray absorption spectroscopy in the middle, and XPS. We concluded many years ago that the HPHT material, though it's on the nanoscale, is basically just like a single crystal diamond. Here's a single crystal diamond slab. Here's our oxidized HPHT nanodiamonds. There's some additional features on the left-hand side that we believe are caused by Pandy chains or the reconstruction of the diamond surface. The XAS, we were able to see the diamond core hole exciton for the first time with nanoscale diamond, and that's at 289 EV. The main idea, though, is that alcohols are the most predominant surface group on our diamond, in contrast to detonation diamond, which people would say usually has carboxylic acids. And we can use XPS to reinforce that and show that mostly single carbon-oxygen bonds and very few C double bond O's are on the surface. So it leads us to this picture. And I think this is an important aspect of this work. A carboxylated surface is not favored due to triple dangling bond carbon sites. In order to have a carboxylic acid, this carbon needs to only be bound by one carbon-carbon bond. And decarboxylation occurs during oxidation at high temperature. This bond is broken and the CO2 will leave the surface. Instead, the way we should be viewing it is that we've got this type of surface where we mostly have alcohols and the occasional carboxylic acid on steps and facets and on edges of our crystallite. And we would say the alcohol-rich surface is favored due to saturation of single dangling bonds on the 111 surfaces And this is common in bulk diamond. And I can share with you many pieces of literature that show that alcohols are readily found on bulk diamond surfaces. And of course, we've got the NV that's hanging out right there. So at San Jose State, I have multiple research thrusts on diamond. We've got the amine research thrust, our silica chemistry thrust, and boron thrust. For today, I'll be focusing most on the silica chemistry and the boron chemistry. Previously, Olga had hosted a talk about the amine chemistry, and I won't spend much time talking about that today. The boron chemistry, it's basically we're trying to remove the alcohols to generate a metastable bromine surface. We come in with a nucleophile, in this case amines, generate a new amine rich surface, and then those amines are very, very good at linking to other molecules. In this particular case, we use folic acid. Why do we care about folic acid? Well, in cancerous cells, folate receptors are overexpressed in cancer cells. So if you wanted to confirm that you've done this conjugation, you could use a cancer cell line, a HeLa cell line, to be able to confirm that you have an increase in photoluminescence from your NVs. And of course, we use a series of different spectroscopic techniques to verify that our chemistry has worked: XAS, X-ray emission, and photo emission spectroscopies, as well as FTIR. A lot of this chemistry is done in air-free conditions, so we're in the glove box and on the Schlink line quite often, and my researchers are there setting up those experiments. Similar to what Olga was prefacing earlier in the talk, we really want to focus on 3 key techniques: our X-ray absorption, X-ray photoelectron spectroscopy, and our diffuse reflectance, FTIR. And of course, all of the other techniques complement our understanding of the HPHT nanodiamonds. But XAS, XPS, and drifts are our bread and butter. We can do XAS at SSRL, which is on the SLAC campus right by Stanford. It's only 25 minutes away. So we've got an advantage. If people drop their beam times, we can hop on and get up there to use the synchrotron because we're local. And so when we go, we use beam lines 8-2 and 10-1. The energies of the incoming photons are between 100 to 1300 EV, giving us access to all the low Z elements: boron, carbon, nitrogen, oxygen, and fluorine, as well as metal centers as well. On the right-hand side are pictures of my researchers controlling the experiments at beamline 8-2 and 10-1. So what is XAS? Well, XAS is an absorption technique which relies on transitions between 1s and p projected states. So the angular momentum has to change. So you go from s to p or p to d orbital. That angular momentum has to change by 1. But because it's a Auger-related technique, you get information both at the surface and from the bulk of the material. And on the left-hand side, you can see that transition of those core level electrons to some bound state. And I'll get into some of the details of XAS. Of course, you get that transition, and those available unoccupied states then host an electron, and we can get a photocurrent from our sample. Now, what's great about being at SSRL is they have hosted a number of different new tools. This is the transition edge sensor. It is basically a SQUID. It's a superconducting sensor which has background-free X-ray detection and relies there on the transition edge. As an X-ray hits the detector, it slightly raises the temperature, which drastically changes the resistance, which then changes the current along this array of detectors, and therefore you can have an amazing level of specificity while getting all X-rays of all energies at the same time. What does this produce? You can get something like this. This is a resonant inelastic X-ray scattering map. So you would go ahead and change the excitation energy while looking at the emission energy on your system. The unoccupied density of states is provided by our partial fluorescence yield XAS. So you integrate counts vertically. If we want to know about the occupied density of states, our ground state orbitals, then you integrate your counts to generate your X-ray emission spectroscopy data set. So you get almost everything all at the same time. So it's quite powerful. Once you've integrated, you get spectra like this, which can then confirm the type of chemistry that's on the surface of your diamond or whatever material you happen to be looking at. In this particular case, we're focusing on nitrogen groups on the surface of high pressure, high temperature diamond. So if you want to go back and look at that paper, the title of the paper is right there. And if you have any questions about that work, just let me know and I'd be happy to talk to you offline about it. Team Amin has done a great job with that, and we ended up getting some cover art for Journal of Physical Chemistry letters. So the heart of one piece of the talk today, which I think is of interest to atomists and other people in the room, is silica chemistry. And so the portion of this talk is silica chemistry, XAS spectroscopy, and the suppression of the diamond core hole exciton. And I'll get right into it. But before I get into some details, I want everybody to be highlighted to this particular work, which is on the archive out of Peter Mauer's group. We had our paper recently accepted. Peter reached out, told me about his work here, and I talked with Peter and his researcher, Yuri Svi, and I think I can have a decent explanation of why they see a lot of this enhancement in their T2 and T1 times based on the removal of electronic states during the silica chemistry. And so if anybody does SiO2 chemistry, I think this is an important aspect. So when we look at the surface of the diamond and we're doing silica chemistry, we start with this material, TEOS, or tetraethyl orthosilicate. It gets hydrolyzed to form tetrahydroxysilane. Then our alcohol groups on the surface of the diamond do a nucleophilic attack. You have a leaving group of water, and you form a silyl ether bond, a carbon-oxygen silicon bond. It's a polymerization reaction, condensation reaction, and water continues to leave, and you can prime the surface and continue to grow silica. And then when you finish that chemistry, you can then decorate the surface with polyethylene glycol or amines or any number of different functional groups. But what happens to the diamond during that process? And is my picture in the middle of the alcohols being involved accurate? You know, you should be suspicious of that. What isn't suspicious is that we can use electron microscopy to validate that we have SiO2 on the surface. This is before, this is after the growth. We can verify is on these edges of our HPHT diamond. You can get it down to 2 nanometers or less, and you have this jagged looking material with a kind of your light coating occurring there. But it's quite versatile, and people for many, many years have used silica chemistry on a number of nanomaterials, including quantum dots, gold, silver nanoparticles, and the like. So when we do our chemistry, we end up with this level of control. If we wish to stop the silica chemistry, we just finish it after a certain time, and then we go through the purification process. And we can get a range somewhere between 2 nanometers to 30 nanometers. And what you'll notice is the thicker the shell, the more circular the particles become. And this has repercussions in endo and exocytosis that Peter Sigler and others have found out many, many years ago. So this is a key aspect that I want everybody to pay attention to right here. So we've got a kind of a new look of what a carboxylic acid terminated diamond would look like. We do our acid-base acid chemistry. We have few alcohols. You can see right here that we have very few alcohols here in our CO stretching mode. And we have mostly carboxylic acids, which are seen at 1780. But if we were to do our silica chemistry without TEOS, these alcohols reemerge. So I believe that we've got a metastable Pandy chain on the surface. These hydroxide ions come in, rehydroxylate the surface, and then are used during this silica chemistry growth. Again, you leave the water, you create your carbon-oxygen silicon bond, and you continue on with your chemistry, and the growth proceeds. What's interesting is our carboxylic acids end up becoming lost during the silica chemistry, and that can be a discussion for another day. But I think that's very, very important for us to understand the mechanism for the growth of our silica. And so I think that was one of the reasons that Peter reached out, is that this might have been a key aspect that he wanted to explain in his work. So again, this is metastable, so we could reverse it. We could add a base, our ethanol, ammonium hydroxide, and water to rehydroxylate. And if we wanted to go back to our carboxylic acid and purge the alcohols off, we would go ahead and do an acid treatment. And usually people do a 0.1 molar HCl treatment for about 24 hours, and then you get what's known as a carboxylic acid rich sample. And it's about 7% of acids across the surface of our HPHT. So this is important to reverse the process based on simple chemistry. So why is this important? Well, if we can go ahead and eliminate some of these surface states from C double bond O, like carboxylic acids, those reside within the band gap of our diamond. And I would highlight this particular paper by Tristan Petit, where they use a number of different surface-related techniques to basically look at charge injection and the absorption of light in their diamond samples. For us, I want you to look here at some oxygen XAS, where we've got our oxygen-rich diamond, but it's alcohols, and we don't have C double bond O. We then do our chemistry to put in the acid, and we now have our pi star C double bond O states, which reside here inside of the band gap. Then we generate our silica shell. Those states are now removed. You've cleaned the surface of unoccupied surface states, which can host electrons. And then we can go ahead and do some chemistry and put those carboxylic acids back on by using silane chemistry. And then we can use that for conjugation protocols and everything else that we need to do if we want to have targeted biolabeling. But I really want folks to look at the contrast between the green, orange, and red data sets. And the main idea is this peak in this area is directly correlated to our unoccupied surface states that we see in the diagram on the left-hand side. So we wanted to be able to readily change that silica shell because we wanted to put them into cells and control the endo and exocytosis rates. And in the process, we ended up seeing that our diamond XAS spectra, this fingerprint spectra, would readily change. The thicker the shell became, the less diamond information we would get. And as we go from A, B, C, D, E, and F, we end up completely suppressing the information from the diamond core. And the question is, well, how far into the diamond can we look? And we can go ahead and look at our TEY data, the amount of electrons coming from our sample. We end up just looking at the ratio, and then we can plot that as a function of SiO2 thickness, take natural log, and end up getting an approximation of the probe depth that we can see into the diamond through our silica chemistry in this overlayer of the core shell. And it's about 15 nanometers into the sample. And I think the important thing is we can use other metal oxides. It doesn't have to be SiO2. We could do manganese oxide, iron oxide, TiO2, any number of different chemistries for metal oxides can be used. We just have to be creative and do the work to generate those systems. But to the details, what is Auger? Auger is an impact mechanism in which excitons collide. You transfer energy from one exciton to the next. That electron is then ejected from the system, but that's not what generates our XAS data. It's actually our secondary inelastic X-rays that percolate to the surface. You have one Auger electron that then collides and loses energy through the crystal lattice and eventually gets to the surface. You can look at the reference on the right-hand side for more detail. What's interesting is that the lower the energy of that electron, the longer its inelastic mean free path. So if it's a low energy inelastic electron, it can continue to percolate up to the surface to be detected during XAS. and the number of actual inelastic electrons that are generated, well, it's about 40 per Auger electrons. And it happens within the first 100 femtoseconds of this process. So it acts as a way of having escaped diamond information occurring. We can go ahead and use CESA, which was invented by researchers at NIST, to look at this Auger process and confirm that the thicker the SiO2, the less information we should get from our Auger electrons, which are here in the 240 to 270 range. And so everything was fairly consistent with this mechanism and the ability for these Auger electrons to be able to percolate up to the surface. When we look at the system, I think for the chemists in the room and for those who are interested in nitrogen vacancy center coherence times, it's really about the mechanism. But we'll just kind of have these concluding statements. The silica growth on diamond cores is initiated by alcohols, not by the carboxylic acids, which are originally on the surface. The core hole exciton can be suppressed. The probe depth can be found to be about 15 nanometers, and inelastic Auger electrons are the main source of our total electron yield. Importantly, we're removing mid-gap states that may increase NV spin coherence times, which I think Peter Maurer and his group has confirmed, which is nice because I wrote a proposal which was rejected and they said it wouldn't work. And Peter's Maurer's group has shown that it has worked. So that reviewer was wrong. And then in the future, I would say, let's use these alcohols to grow new metal oxide cap diamond systems. Can we do type 1 and type 2 band structures similar to what we've done for years with cadmium selenide, zinc sulfide core shell, and the like? And I think maybe we'll get a new picture of tunability with our diamond substrate. So that's a challenge that I set out to the field for us to get more creative. Okay, and of course, I didn't do the work. All of my researchers did the work, and they've done a fantastic job. And again, we got a little bit of cover art, and that's in ACS Nanoscience Gold. So please go ahead and look at that paper. Now, a new bit of chemistry that we've been working on, and this is going to be submitted to a special edition that Olga is the editor for, is dealing with boron chemistry on the surface of diamond. And so I call this section Boron Chemistry and Consequences of Fluxionality. And most people in the room don't know what fluxionality is, and I didn't either until I started doing boron chemistry. So let's get into it. What does boron have that's unique, and what can you do with 3 electrons? Well, boron is the 5th element of the periodic table, but only has 3 valence electrons. Therefore, it's electron deficient, and it ends up generating some very, very unique bonding environments. And theoretically and in practice with materials, it can be described by a process called fluxionality. That's the rapid rearrangement of degenerate chemical species. So basically, these bonding environments, you could have 4, 5, 6, or 7 bonding bonds being formed around one boron center, but they are all degenerate in energy. So it's something similar to like a superposition of chemical bonding. What's interesting about boron is a single bond is delocalized. And that's unique. In carbon, of course, we need an sp2 or sp bond to have delocalized pi bonding. Boron does it on its own because of its unique bonding environment. And I would recommend you look at the paper that you can see over there on the right-hand side. Why do we care about boron? Well, it's an analog to carbon. People have made boraphene. It has unique electronic structures, which can then be used in optoelectronics and electronic devices. This was only recently realized to get our single and bilayers of boraphene, and much of the DFT was confirmed experimentally. On the right-hand side, you can see a little bit of XPS, where boron-oxygen bonds and boron-boron bonds have been confirmed, and I'll use a little bit of XPS in the near future to confirm our boron chemistry on diamond. But why do we care? Well, what's interesting is that if we can go ahead and put boron on the surface, we could use it not only for NV sensing, but also for boron neutron capture therapy. Boron neutron capture therapy is a way of treating glioblastomas, highly sensitive brain cancers that can't be treated any other ways. And so boron clusters are injected into the brain, and then you irradiate the patient with neutrons. The neutrons are only collected and harvested by boron 10. There is literally a nuclear reaction which generates lithium-7 and alpha particles. Those alpha particles then destroy and heat up localized cancer cells, and there is a high level of efficacy in this therapy for reducing the size of boron, of cancerous brain tissue. But boron nanostructures are typically done with borane gas and high power lasers. So many folks have stayed away from it for many years, but now there's been an increase in the synthesis techniques. So our method, which I'm about to show you, enables us to template this boron onto our nanodiamonds at standard temperatures and pressures. So we hope to be able to expand this going forward. Here's another cartoon. Again, we're using this alcohol-rich diamond, which is doing a nucleophilic attack on our boron center. You would have a leaving group of hydrogen bromide. You've now formed a carbon-oxygen boron bond, which is an organoborate. The chemistry continues, forming some boron-boron bonds, and some of the remaining bromide or chloride groups are still dangling on the surface, and then you can go ahead and continue on with your chemistry. In the bottom of the slide, you'll notice that all of these precursors are trigonal. This is highly reactive and is an electrophile, and we found out that all of these do a similar level of chemistry. Now, the reactivity increases with the halides, but these other types of ligands on the surface, whether or not it's an ethyl or an ethoxy group, are also reactive to the diamond surface. And that's because these guys are planar and the boron center is highly electrophilic. What vibrational signatures can we observe to rapidly screen for these signatures? We go ahead and use air-free drifts. We have a little chamber that we can bring out of the glove box. And if we do DDR3, BCl3, or BH3 chemistry, we can see this alcohol stretching mode shift, letting us know that something has happened on the diamond surface. And we show that a new carbon-oxygen boron bond shifts almost by 75 wave numbers to about 1025, 1015. And, you know, vibrational spectroscopy is quick. So it allows you to screen samples nicely without ever having to use the synchrotron or an XPS. I think this is an important aspect of the work, that if we were to compare to other boron-containing compounds, borax, boric acid, which is BOH3 or trimethyl boron, we've got kind of a mixture of vibrational modes, which may be due to both trigonal BO and tetrahedral boron oxygen bonding environments. So when you look at the literature, just say if we're around 1500, those are trigonal. And if we end up going to lower numbers like 1100 or 1000, those are our tetraagonal bonding environments for boron oxygen. So we take these, we look at them with electron microscopy. This is before. Many of you have seen similar types of SEM images. We then do our chemistry and we end up with this odd stuff. We have this layering, we can barely see what's going on. Why is it diffuse? Why does it look like the diamond has become rounded? We can end up picking out single nanoparticles, and we can see those on the left-hand side, where we can see like a 50 nanometer particle, again, very diffuse. We can use energy dispersive X-ray spectroscopy to confirm that we've got carbon, maybe a little bit of boron, but you shouldn't really trust me on that, and then quite a bit of oxygen that's remaining on the surface. If we do EDS, The problem is, folks, is that big carbon signal is right by the boron. And so Virginia Alto at the molecular foundry would say, no way, we're not going to use EDS to confirm that boron is on the surface because it's too embedded on this leading edge of the carbon. So then we have to use surface sensitive techniques like XPS, like X-ray absorption spectroscopy to confirm what's going on. You'll notice, though, that we do have some information from the bromine. So some of these bromines remain on the surface of the diamond. You would think that they're still bound to the boron, but we don't quite know that. If we use XPS, we can do survey scans, which you can see on the left-hand side. I've got a number of control samples, boron carbide and boron, but all of the action is right here. This is our core level B1S emission. If we zoom in on the right-hand side, this is where we would see a elemental boron, a powder. This is boron carbide, and then this is the structure of our BBr3, BCl3, and BH3 treated sample. You'll notice that boron is right here around about 188 EV. And then as you get to oxides, you move to the left to about 193. We see some information at about 182, but I think that's more controversial. And some folks have said it's a BH-1, but you shouldn't test it. Most of the information that's related should be between 188 and 193 EV. So this would be boron carbon, boron, and boron oxygen related bonds. And the more that the boron is oxidized, the farther that peak would shift from +1 to +2 to +3, ranging from about 190 EV to about 190. So we're putting that into summary. If we looked at the carbon, again, we get this mixture. It's not looking exactly like boron carbide, but it's sort of this agglomeration. If we look at our original starting material and then our BBr3, BCl3, and BH3 related material, the one aspect that comes up is that we get this new edge for boron carbon bonds, which is highly unusual. We weren't expecting this. So maybe our trigonal boron is actually quenching some of these dangling bonds on the surface of our material and forming a direct boron carbon bond, which was a unique discovery of this work. So basically quenching any of these electrons invasive on a nanocrystal surface. Again, we go to the synchrotron and we go ahead and we look at our two edges. On the left-hand side, we're looking at boron. And so you're only looking at boron at that time. On the right-hand side, you're only looking at carbon. Again, we go ahead and use a combination of our samples, BBr3 and BCl3 related samples, and then compare those to our controls. This is boron carbide, elemental boron, and our other controls, and this is boric acid right here. And so what we see is a mixture. It's heterogeneous. Again, it kind of looks like boron carbide, but not exactly. You've got evidence, again, of a boron carbon bond, boron bonds, and this trigonal and tetrahedral bonding environment. So it's quite unique. And then as you go to higher energies, the sigma star states, so you can consider these are more of our delocalized pi bonding, and then these are our sigma-like on the axis between boron and oxygen bond formation. Now, if we look at diamond, and this is the cool thing about our XAS, is we can both see the boron coating and the diamond simultaneously. We can compare it to boron carbide, and we get these new states that are in the edge. So when we do the boron chemistry, we seem to have introduced new mid-gap states. This could be bad for spin coherence measurements, but I think it's worth pursuing both in the bulk and in our nanoscale material simultaneously. So just throwing those ideas out to the community. So why is this unique? Well, a couple of years ago, folks actually found out that this boron-oxygen environment on diamond makes it N-type. So it has an N-type surface conducting layer, which then we might be able to use STM or make devices that are N-type conducting. And what's unique about this is that in this study, they used boron-doped diamond, which of course is a P-type dopant in diamond, commonly used for tribiology and other electrochemistry applications, but they found that boron-oxygen mixed states allowed for conductivity to occur. And so again, I would highlight this paper as a way to kind of summarize the connection between bulk diamond crystallites and what we're seeing on the nanoscale as well. Okay, so as we conclude the boron section, we can say boron terminated nanoparticles can be synthesized at standard temperature and pressure using alcohol terminated nanodiamonds and trigonal boron precursors. The boron chemistry appears to self-terminate in a similar way to atomic layer deposition. It's ultra thin. We've estimated that we have about 1% atomic concentration. And so if we look on the right-hand side, it's kind of a picture like this that we can begin to sort of glean from our data set. And some questions that we should have. Does boron termination of NV diamonds affect their NV center properties, spin coherence, and the like? Can we build a thicker layer of boron on the nanodiamonds, which can then be used for boron neutron capture therapy? Could we use them on detonation diamond? Probably. Does it change the Fermi energy? And can we use UPS measurements to see how our Fermi energy is changed through the use of our boron chemistry? And we should improve the characterization of these boron nanoparticles and gain a better understanding of the reaction mechanism. Okay. Of course, again, I didn't do the work. My research team has spent countless hours doing this work. And so I say thank you. And of course, Virginia Alto at the Foundry, Dennis Nordland and Sanjin Lee at SSRL. I'm indebted to them, as well as our funding sources through the federal government, NIH, DOD, and NSF, and of course, our partners at the Department of Energy. But a big thank you to Professor Carlos Mariles and everyone who I've worked with here with the Ideals Crest at City College, Dr. Kangju, Dr. Daniela Pagliero, Dr. Gabriel Lopez Morales, and of course, Ideals Crest Director Maria Tamargo, who is hosting me here at City College. And my family and I have liked it so much in New York, we kind of think about staying. So with that, I say thank you so much. And these are pictures of the professor and his family on vacation in Uganda and in El Salvador. So thank you very much for your time, and I'll take any questions you have.
Thank you so much. It's so interesting talk. Yeah, it's such in-depth chemistry, and you try to nail down every aspect of a subject of your study. It's very impressive. So we are open for questions.
Hi, Abraham. Hey, great talk. I had just a couple, one quick question, and I guess a comment. So I'll additionally give you a secondary confirmation on that silica shell coating and the relaxation properties and things being enhanced. We just, maybe around about the same time, that paper on the archive from Peter Mauer's group, we were coincidentally just doing the same thing, and I saw similar enhancement of these relaxation times and the suppression of the CPR. So yeah, your idea for that proposal was good. Yeah. So
Wonderful.
Yeah. I guess my other question is, how do you think in terms of these NV coherence properties, how much does having this thin dielectric layer in terms of screening, say, electric charge interactions on the surface versus, I guess what you were showing is this, as I understand, this band bending near the surface as the mechanism of how these maybe coherence times are increased. So I guess there's two mechanisms maybe, or two processes.
Yeah, so the overall the overall like hosting of electronic noise on the surface of the diamond, to your point, maybe it's getting screened by the silica, but the silica is ultra thin. So I guess we'd have to model it. And I think Peter Maurer did a wonderful job summarizing some of that band bending and the removal of some of these occupied states. And I think what we can see using our spectroscopy is that, again, if in fact it's a combination of both doing a band bending mechanism to remove electronic density, and you're also shielding some sort of a transient, static charge in conjunction with these mid-gap states, I think we're much, much better to understanding like the real decoherence mechanism. Because Nicholas, when I wrote this proposal, everybody said, well, the nitrogen inside of the HPHT nanodiamonds is what's going to control it. So even if you do the surface chemistry, you're never going to be able to deconvolve it. And, Nick, are you at NC State?
Well, as of yesterday, I guess I defended the PhD, so I'll be back at Adamus very soon. But yeah, I'm also technically it's sitting in NC State still. So
congratulations on defending your thesis and your PhD. And I mean, it's a great time to have just finished up, because I mean, in my opinion, this is like just the beginning. We should be able to take this type of chemistry. And remember, I did the SiO2 chemistry just like you did at room temperature and open air conditions. We can take all of these metal oxide salts, and we've tried TiO2 in the past, but we didn't put as much energy into it as we needed. And so you could look at a host of different catalogs of metal oxide salts and start running the gamut and get creative. And, again, are we going to do a band 1 alignment? Is it going to be offset like band 2? Can we begin to control where electron and hole wave functions are going to reside? Like all of these things that we learned about with quantum dots, I think we should be able to apply with our diamond substrates as well.
Yeah, I thought it would be cool to look at if you can compare the silica coating on HPHT diamond and then detonation diamond, because of course, like the shape of the particles is quite different for detonation diamond. So it maybe gives some I was thinking if there's some way to like suppress the surface noise on detonation diamond to get some ability to look inside that the diamond, this detonation diamond, more than you can. But anyways, yeah, just some idea.
No, Nick, it's a fantastic idea, because I think one of the things that's always killed the det diamond is not only do you have like many, many different surface groups, but I would argue that more of this sp2 dangling bonds, Alistair Stacey would say that they're primal sp2. If you went back in the literature, you would call it a Pandy chain, but it's basically a sp3 hybridized bond that doesn't have anything quenching that bond. And so it goes ahead and makes this metastable sp2-like structure. And so if we can go ahead and really clean up that surface on det diamond, on HPHT, and on bulk diamond as well, because there's absolutely nothing in the literature that says that our Pandy chains or our primal sp2 defects aren't there. And so this is an area in which we should pay attention. And you can use Raman spectroscopy, you can use XAS to be able to begin to dive in to what sp2 groups are going to do. And I think that was a really interesting and simple control that we did. Here's our carboxylic acid related particles. We add in everything that we had before: ethanol, ammonium hydroxide, and a little splash of water. And now all of a sudden our alcohols spring back to life. Isn't that interesting? And then if we add TEOS, of course, we grow the silica shell, the carboxylic acids go away and we can go on with the rest of the story. So it's a combination, I think, of not only the carbon-oxygen bonds that are there, but the non-carbon oxygen, the carbon-carbon moieties that remain after we do some of our chemistry, like the acid-base acid chemistry.
Yeah. Oh, thank you. Yeah, great talk. Yeah.
Yeah, thank you.
Hey, while you're on this slide, actually, very, very nice. I thank you for the talk. You're always very, I love your chemical approach.
Thanks.
Background myself, it's always very precise and very, very thorough. So I actually love your talks. But on this slide, you made a comment about the carboxylic acid and kind of didn't really mechanistically push too much more on that. So could you talk a little bit more about actually how the CO2 is leaving?
So there's some aspects in the literature, Marco, that talk about decarboxylation with silicates. And we referenced it in the quantum diamonds at the beach paper, but it makes sense. There's really no evidence that the carboxylic acids are there by drifts, by XPS and XAS. So maybe there's some sort of nucleophilic attack that's occurring, and then this ends up creating a leaving group.
Yeah.
Basically it's a silicate, and there's all kinds of different stuff in the literature, almost in like geochemistry journals, that talk about, acids and silicates and how they do all of their funky chemistry together. And maybe we're getting a picture into that with another geologic sample. I mean, it happens to be diamond, but this probably happens more readily than we think about with silicates.
Yeah, that's a very cool perspective. Yeah, thank you. I'll read a little bit more about that.
Yeah, I can get you that particular paper. It's in there somewhere, but I'll
Yeah, no, actually, I have to look back at it. Yeah, to see that discussion point, because I think it's very interesting.
And to be honest, I have no idea why it happens. It was an observation, and we can talk about it at another time.
That's the first step, though. That's the first step. No, because it is clearly not there from the data. So yeah, it's cool. Thank you.
Yeah, of course. Anytime.
Please feel free to ask more questions. I have a couple of questions. So, Abby, when these boron decorated diamonds with NV centers will be produced and its quantum properties measured, what's the plan?
Well, I think one of the midterm ideas is to take, so element 6 has macles. So these macles are 1-1 terminated diamond. And I would like to see if we can just do the chemistry on the macles. Do they create this ultra thin boron coating? And then, of course, try it with the HPHT diamond, with atomist diamond, and see, does the photoluminescence change? Is it increased? Is it decreased? Do the T2 and T1 times become perturbed? At this stage, nobody's gone anywhere close to this type of chemistry, but we do know that we can put them in water and the boron groups remain there. And we can also put them into non-polar solvents like toluene and chloride, chlorinated benzene, chlorobenzene, and other solvents. So I think it's to be seen, but I would, at least based on the XAS data, I would assume that the boron groups would act as an electron trap. So, it may end up.
Yeah, maybe opposite.
It could trap charge, but at the same time, maybe the frequencies of those trap charges will be much different than dangling bonds in other groups. And so you could have boron oxygen bonds on the surface and basically minimize that spin bath by looking at different frequencies. Stuff that Natalie De Leon and others have done with the single and double quantum measurements that they had looked at in 2019. So.
Because it seems that, say, your motivation over these boron trapped neutrons by boron in this therapy, tumor therapy, right? Then having diamonds, perhaps measuring temperature of tumors might be of importance, having diamonds with boron on surface, but also being able to measure temperature. I don't know if temperature, it's probably temperature is not important, right, in neutron therapy. I'm just guessing what sensing property of diamond can be useful in that type of therapy.
Yeah, it's
what they monitor.
Yeah, it's hard to say where that particular technology would go. As far as I know, and of course I'm a non-expert, but the main holdup with BNCT is making sure that the boron clusters get through the blood-brain barrier and absorbed by the cancerous cells. So any type of tuning that we can do to change the morphology, the aspect ratio of these nanomaterials, perhaps the uptake into cancerous cells can be increased, and therefore the patient would have to have less boron clusters injected into their brain prior to the therapy. You know, it's again, it's an area that I'm not an expert in, but I can understand that, again, surface chemistry plays a role, nanomaterial surface to volume ratio plays a role, and I think you know, diamond as a non-cytotoxic host and a templating material is another kind of exciting avenue to explore.
Thank you. More questions? Maybe another very short question. You mentioned role of diamond in silica shape in endocytosis. Can you elaborate a little bit more on that important aspect?
So Peter Sigler had collaborated with a group in Taiwan some years ago, and I believe it was a Science Advances paper. And what it basically showed was that the thickness of the SiO2 then determined how long the particles would be inside of the cytosol. So imagine this, the silica-coated diamond, if it's thin, is more jagged. It gets endocytosed, is brought in to the cell, but then can break out of the endosome and stay inside of the cells for longer. Contrast that with a thicker silica shell, which is more rounded. Those ones will be endocytosed and then eventually expelled during exocytosis in much the same way that you would, you know, with any other package that gets brought across the cell membrane. And so this was always exciting to me because I'm like, okay, well, we want a NV sensor to stay in cells and tissues for as long as possible. This work is telling us that we should really have a thin shell. The thin shell then would allow you to break through the endosome, and you could do long-term imaging inside of your cell line without having to have your quantum sensor removed again through exocytosis.
Okay, thank you. And maybe also if you can briefly comment on longevity and robustness of silica shells on diamond surface. Say, I know they should be preserved in ethanol, it seems, for example, to have them robust for a few months. Shelf life, so shelf life related question to silica shell.
Yeah, so typically in the lab, we would lyophilize these guys and keep them dry. And then once we wanted to disperse them, then we'd go ahead and put them in water or ethanol, decorate the surface, and then go on with things. I think as a chemist, it makes sense that the chemistry that goes from left to right can also go right to left. You know, and we need to remember that. So you can have precipitation and these bonds forming, but they can also go in the opposite direction. and create the starting materials, our tetrahydroxysilane. And so depending on the robustness, imagine this, Olga, we do our silica chemistry and then we anneal the sample. We make them more crystalline, less amorphous. And if they're crystalline, they should be more robust against dissolution. They shouldn't go back towards tetrahydroxysilane. They should stay with their SiO2 bonds. And so we've never pursued that. I've thought about it for years. Like, let's just take silica coated, do a high temperature anneal. You could even do it in nitrogen, or you could do it in oxygen or open air conditions, and then do the remaining portion of your chemistry to decorate your polyethylene glycols and your amines and everything else that you need. But you would like harden the shell, get the shell crystalline.
And you're thinking about temperature, say, to 200 centigrades to 300, because I'm just thinking, say, a regular glass, say, how you can treat regular glass, say, it's dangerous above, say, borosilicate glass. I just got few glass broken, melted in furnace.
That's very high temp though, right? We're talking about 1100 C, 1200 C. So, I mean, just imagine, you put a little bit more thermal energy into your system, you begin to repair bonds, they get annealed and then re-relaxed during the cooling process. And who knows, maybe even if we did TEM, I mean, this would be, a paper is take the silica, you do TEM, then you do the annealing steps at 100, 200, 300, 400, redo your TEM study, and do you begin to see crystallographic orientation of SiO2?
Yeah, it would be very interesting experiment, and then to check also robustness, shelf life, and everything.
Yeah, and
again from practical perspectives,
exactly. And then you could do a dissolution study, like, hey, after doing an annealing step at 300 C, we went ahead and put them in water for 2 months and didn't see any change. The silica remained robust. We didn't have any issues with the thinning of the shells, so on and so forth.
And also to remeasure T1 and T2 would be interesting.
And again, yes, T1 and T2. I don't think Peter did any post-treatment. He probably did a silica shell growth at room temp, and he used the PVP protocol as I think, and then went on with the rest of that particular study. But there's nothing stopping us from a heat treat. Absolutely.
Yeah, maybe we can do collaborative work and assign Nicholas next task to check some.
What's interesting is, and I'm not sure if any of the silica chemistry folks are out there, but besides Nicholas, but in the route that we use, which we borrowed from Peter Sigler, we don't add PVP. All we use is TOS, a majority of ethanol and ammonium hydroxide, and a little splash of water. So it's very clean. There's very, very few things that go in there. We don't need a polymer, and we can get a high level of control on the thickness of the SiO2.
Okay, any more questions from the audience? Then I would like again to thank Abraham today for great presentation, very exciting, and look forward to interact more.
Absolutely. Olga, let me know if you want to talk about any chemistry going into the near future. Oh, I see Roger Terrell there. Hey, Roger. Nice to see Roger. Yeah, just let me know if you have any ideas. If you see something that you want to readily discuss with the silica chemistry, I'd be more than happy to jump on a call with you and lend some ideas.
Okay, great. Yeah, definitely we will do.
Okay, very good.
Okay, bye.
All right, ciao for now. Bye.